Welcome back. In this video we're going to focus on the motivation behind what we call the null space and the column space of a matrix A. I want to start by talking about why this matters. We saw that given any matrix A, which has m rows and n columns, we can define three very related problems. In our case we call this the matrix vector multiplication problem, where we were given the matrix, we were given a vector, and we tried to get the output vector associated with that. We also saw that the inverse of this problem was known as the linear systems problem. And then the final related piece in this theme was known as the least squares problem, where our job was to minimize the residual between the vector B and the set of all possible outputs with A. And in this case we said this minimization was occurring over our input space Rn. We saw that there was a subtle difference between linear systems problems and least squares problems, and that difference really had to do with the space that B was in. All three of these problems are connected by a common mapping, and we say that each matrix defined an associated function called a linear transformation, which is given by matrix vector multiplication. In all three of these cases, this function has domain Rn and codomain Rm. What we saw in the linear systems problem is that matrix vector multiplication problem, linear systems problem, LSP1 because it's the first of them, least squares problems, LSP2 because it's the second involved problem. What we saw in the linear systems problem was AX equal to B if and only if B can be written as a linear combination of columns of A. So in other words, this linear systems problem has a solution if and only if B can be written as a linear combination of the columns of A, which another way to say that is B is in the span of the columns of A. One thing that we're going to see is in some least squares problems, what happens if B is not in the span? How do we solve that type of problem? Well, one of the major ideas that we're going to look at, if you look at what we call the span of the columns of A, so let's say that this rectangular two-dimensional thing was the span of the columns of A, and then B did not completely lie within that. Well, the idea of minimizing, what we're going to do is we're going to project B down onto this space. And we'll call that projection B hat. And we'll call the difference between the actual vector V and its projection, we'll call that R, which is just what's known as the residual. If this projection is done in such a way that we maintain orthogonality, we say that the length of this residual vector is minimized. Thus, finding the orthogonal projection onto the span of the columns is the solution to the least squares problem. It just so happens, in order to solve this problem well, we need to introduce a bunch of technology to help us talk about this. And that technology will be known as the null space and the column space. So the major idea behind these null space and the column space is we're adding some complexity. We're developing new theory so that when we make the jump from solving least squares, linear systems problems to solving least squares problems, we can rely on this powerful new technology to very, very quickly find the solution that we want. More on that later. For now, let's focus on defining the null space and the column space associated with any matrix. See you in the next video.